Hi, I'm Garrett. This is lab group 3A. In this lab we're going to be eventually testing the MTF of a lens, but first to get the initial setup, this is very similar to previous week's labs where we align a Heaney laser along the short rail, and then we fold the beam by 90 degrees just using a regular flat plane mirror so that we have a nice aligned laser along this long rail here, marked off the spot, and then set up a beam expander so that we can get a good end. It's a 20x microscope with a numerical aperture of 0.4. We're using a 25 micron pinhole to clean the beam and a collimating lens that's a 2-inch diameter, which will give us an adequate expansion ratio. We've actually just overfilled the aperture of the testing lens. And then we test for collimation and it's good. So once that setup is all in place, we're going to observe diffraction effects. So we place an aperture and we stop it down to its, an adjustable aperture, and we stop it down to its smallest setting, which is a radius of about 1/32 of an inch. Using that number and the wavelength of the Heaney laser, 632.8 nanometers, we calculate the distance to NF, or E equals 1, which corresponds to a half wave of OPD error. Our calculations suggest 995 millimeters, but in fact it turned out to be about 1012 millimeters, so it was close. So next what we did is we took a microscope on a 2-axis translation stage. Its numerical aperture is appropriate to capture the whole beam, and we placed it well behind our calculated distance and sort of observed the diffraction effects. You can see here there's a little bit of splotchiness. Nothing's quite perfect. But anyway, so as we sort of move this microscope in, you can see the center spot start to go dimmer, and it's a null pretty much here, and that corresponds to NF equals 1, or half wave OPD. And you see as we keep moving it in, and then we keep moving the microscope, and it's another null, NF equals 2. Now we have a full wave of OPD, and as we keep moving the microscope in, we just keep increasing the number of fringes, and it starts to happen at an increasing rate. And now at this point we're at 6 or 7 fringes. So that's just sort of the general diffraction effects.
Hi, I'm Ryan Kreisberg in Lab Group 3A. So I'm going to talk about Part C very fast. Part C was focused on the black dot method. And what the black dot method does is tells us where the best focus position is. So right now we're at approximately the best focus, and you can see we have a nice clean spot in the middle. So we're going to go to the +1 position, and you can see that our center will get dark. And at its darkest point, we take a measurement of where the microscope is, and we also go in front of the best focus position, and we can see right there is our second spot. And we take these two measurements, and we take the middle position, the average of those two positions, and we take that at multiple aperture sizes to find our very best. Important thing to note about this method is that at the black dot points, it's one wave of wavefront error, or OPD error, and as we increased or decreased the aperture size, as the aperture size got smaller, the distance from the best focus that we saw these points got much larger. So the bigger the spot, the closer to best focus the black dots happen, and the smaller the aperture, the further away. In Part D, we were aiming to create a diffraction limited system, so I'm going to run you through that. Our F number of the system, our EFL was 1,000 millimeters for the small test lens, and our calculated width was of our aperture was 1.61 millimeters, so we had a 621 F number. Then we can use that F number and the wavelength of our laser to find our cutoff frequency of the system, and we came out with 2.5 cycles per millimeter. To find the desired slit width at the edge of our system, at the end of our system, we do 1 over the cutoff frequency, which is about 0.4 millimeters. Then we use all these things to find our desired aperture diameter for this part, and we use the desired area disc diameter of 200 microns to come out with a desired aperture size of 7.6 millimeters. We initially made a calculation error, so we had about a 2 millimeter diameter for the aperture. It didn't affect our stuff too much. We had to extend our rail a little bit to get a longer a longer distance so we could get that back dark spot in the center. But our spot was also bigger, so we were still able to get this desired 200 micron diameter area disk.
Alright, hi. And for this next part of the lab, we were trying to measure the power of the area disk. And so we just previously found the optimal cutoff frequency. We took the inverse of that to find the optimal slit width, which is 0.38. And then we just used a microscope to align this, or not to align it, but to find best focus, plus one wave of defocus and minus one wave of defocus. Once we did that, we took data and plotted it, and I'm going to show you those next. Okay, now we have our line spread functions, as you can see here. So we took power readings and micrometer readings. And for best focus, it's diffraction limited, so we expect it to be a narrow Gaussian pulse shape. And for plus one wave and minus one wave, it's the light is broadening out, so it's taking up a wider area, so hence a broader Gaussian pulse shape. And then